Hello there, Mr. Sutton here, bringing you the Algebra 2 Honors 12-3 lesson on determinants and Cramer's rule. This will be a two-parter. In part 1, we're going to be finding determinants of 2x2 and 3x3 matrices, and also figuring out triangle area using determinants. And then in part 2, we are going to use something called Cramer's rule to solve systems of equations. We'll even get to use the Desmos matrix calculator. We're going to begin this lesson by attempting to define determinants, which are the systematic underpinning of everything that goes on in this lesson. So it turns out determinants are actually a lot easier to calculate than they are to define. What is the determinant of a matrix? I can tell you how to do it, but telling you what it actually is a little bit trickier. But here's my best attempt. The determinant of a matrix, and we can use DET followed by the matrix name, or you can put the whole matrix inside these absolute value looking bars here. The determinant of a matrix is a single value found by subtracting the products of a matrix's diagonals that are going in different directions. So that doesn't really clearly spell out what exactly a determinant is. It's more of a procedural definition, but kind of the big takeaway from this is that a determinant is a single value. Unlike all the other matrix calculations we've done, we're not getting another matrix. We're just getting a single value that kind of represents all the properties of the entire matrix. You could almost think of it as kind of being like the fingerprint for a matrix, but it's not necessarily like every matrix has a unique fingerprint. Some of them can have the same determinant. So let's go into how we actually find this determinant. So in order to find the determinant of a 2x2 matrix, that's what we'll be covering on this slide here, because 3x3 is a little bit different. I said that we find this by subtracting the products of the diagonals. So we're going to, and by the way, I can rewrite this as like absolute value looking matrix here. This is also the determinant. So what we're going to do here is we're going to start at the upper left and we're going to go down and to the right. So this diagonal. So we said products of the diagonals. So we're doing A times D. And we're going to do the product of the diagonal going the other way. That's going from the lower left to the upper right. So CB, we're going to subtract C times B. So it's AD minus CB. And we always go in that order. We always do the top down diagonal first, and then the bottom up diagonal always comes after the subtraction. So with this in mind, pause the video and see if you can figure out the determinant of each of these matrices down here. All right, let's see how that went out. So that went for you. So let's start with part A. So we have the top down diagonal. That's 2 times 4 minus bottom up 1 times 5. So 8 minus 5 just gives us 3. That's it. Now for part B, we do a top down, so negative 2 times 10, and then bottom up, this would be a minus negative 8 times 4, but minus minus gives us a plus, so this will be a plus 8 times 4. So that's negative 20 plus 32, which is going to be 12. Next up, we're going to dive into finding one of these 3x3 determinants. Now, I'm about to show you something that's going to look like a formula. It's going to have all sorts of letters in it, but I'm going to encourage you not to try memorizing it. Instead, try memorizing the process that I use to get there. That's the most important piece here. So, to find a 3x3 determinant, let's say that we're starting with this. So we've got a matrix with some letters to represent all of the 9 spots in here, A, B, C, and we're going down in that fashion. So to find the determinant of this, we're going to copy the first 2 columns, that's ADG and BEH, after the outside of the matrix. So we're just going to cut and paste these first 2 columns out here. Exact copy. The reason we did that is because we're going to be doing some diagonals now, and this allows us to get more diagonals in. So what we're going to do is we're still going to be subtracting some products, but instead of just subtracting one product from another, we're actually going to have 3 products in each diagonal direction that we're going to be adding up and then subtracting. So as I said here, we're going to subtract the sums of three diagonal products. So just to demonstrate what's going on here, we're starting with the top downs just like before. So we have this diagonal, that's AEI, plus this other diagonal product, BFG. And then we have this last diagonal. This is the last unique diagonal here because then we'd be starting over with A again. So this is CDH. We're adding all that in. So these three products are being added together to give us kind of an overall downward diagonal sum. This takes the place of just that one little downward diagonal we had on a 2x2. So things definitely get trickier, a lot more complex when you just make one more dimension here. Let's go the other direction now. So we'll start with G. So we're going bottom up now. So GEC, and we're going to be subtracting the sum of all these ones. So I'll do a minus parentheses with GEC as the first term. And then we've got HFA, adding that in there. And finally this last one, IDB. And this is what it looks like if we were to multiply all of that out, then add those products, and then subtract the two sums. This is our determinant. So it looks like a lot. In practice, we end up kind of calculating these 6 products either on a calculator or in our heads, but show as much work as you want to here. And again, I encourage you to copy or memorize the process for getting this with the diagonals. Don't even try memorizing this thing as a formula. A computer could handle this just fine, but it doesn't work so well for us humans. So with all that in mind, pause the video and see if you can calculate the determinant of this matrix, and feel free to use a calculator for the number crunching part at the end. Alright, so going in each direction. First off, let's copy and paste the first 2 columns over here. And now let's do our top-down diagonals. So we've got 3 times 0 times 1. That's going to be 0 because we have a 0 being multiplied in there. So that's kind of nice. Next, this one, we've got 4 times 6 times negative 2. That's 24 times negative 2, so 48 negative. And next, we've got negative 1 times 2 times negative 3. That's going to be positive 6. And now from all these, we have to subtract the top up or the bottom up diagonals. So we've got negative 2 times 0 times negative 1. We've got a 0 in there, so that zeroes that whole product out, which is nice. So I'm going to do minus parentheses and then 0 is the first thing inside there. Next, we've got negative 3 times 6 times 3. That would be like negative 9 times 6, so negative 54. And lastly, we got 1 times 2 times 4. That's going to be 8. All right, let's do this. You actually don't really need a calculator for this, but feel free to use one. So out here we've got negative 42. In here we've got negative 46, but we have a minus negative 46. So negative 42 plus 46 is going to give us 4. Just 4 for that whole thing. Now you might be saying, wait a sec, go back. I want to do another example with a 3x3 determinant. That was so much fun. Don't worry, you'll get another chance to do one of those, but we're going to sneak it in the context of a new formula, new skill kind of thing. So have you ever wanted to find the area of a triangle? Of course you have. And you've done this in all sorts of situations. Kind of the most universal is maybe you had all 3 sides of a triangle and you used that crazy hero's formula to figure that out. Well, what if you don't have all 3 sides, but what if you have all 3 points of a triangle? You could find all 3 sides using the distance formula and then use herons, but that sounds like a lot of work. So is there a way to just take 3 points that make up the vertices of a triangle, plug them in some formula, and get the area? Actually, there is. So the area of a triangle with the points x1, y1, x2, y2, and x3, y3 is as follows. So the area is going to be, the way I've written it is plus or minus 1/2 times, what are these vertical bars? That is the determinant of a matrix. And this matrix has x1, y1, x2, y2, x3, y3. All the x's are in the first column, all the y's are in the second column, and in this last column, there's just ones, and those are always going to be there no matter what. Those are kind of part of the formula. So you basically just have to plug these points into this matrix, find the determinant, take half of that, and you're good. Now this weird little plus or minus out here, that's there so that we ensure that the result is going to be positive. Because when you take a determinant, you're going to find you might sometimes get negative numbers, and obviously we want triangle area to be a positive value. So just make it positive if it would normally come out negative. So with all that in mind, pause the video and see if you can figure out the area of this triangle. Alright, so first we're going to set up our determinant with the points in there. So we're going to have plus or minus 1/2 times the determinant of, and we're going to have 2, 3, and then 1, and then 3, negative 2, 1, and negative 4, negative 3, 1. So just these 3 points plugged in red here in the first 2 columns with 1s in that third column. So let's go ahead and find that determinant, and we'll do this by hand. No need to use the calculator yet. So again, we're going to be doing our top-down diagonals first, and before we can really start that process, let's cut and paste these first 2 columns and put them over here so that we can get 3 diagonals in each direction. So first diagonal, we've got 2 times negative 2 times 1. That's going to come out to negative 4. And I'll leave this plus or minus 1/2 hanging out here so I don't forget to do it later. The next one, we've got 3 times 1 times negative 4. That's minus 12. And the next one, we've got 1 times 3 times negative 3. That's minus 9. So that takes care of our first direction. Now we'll do the bottom ups. So we've got negative 4 times negative 2 times 1. That's going to be 8. And again, we're going to be subtracting these 3. So I'm going to do minus parentheses, and then I'll have an 8 inside there. Next, I'll do negative 3 times 1 times 2. That's going to be negative 6. And then finally, we've got 1 times 3 times 3, which is 9. So I just need to crunch these numbers to get my answer. For that, I am going to go to Desmos. I don't want to mess around with arithmetic errors. So let me do 1/2, and then I'll multiply this by the following. So we've got negative 4 minus 12 minus 9 minus parentheses 8 minus 6 plus 9, and I'll close those parentheses. Now that would normally come out to negative 18, but this is why we have that plus or minus out there. We're just supposed to choose the positive version of this, the best version of itself. So we'll call that positive 18 for the area of this triangle. So this concludes part 1 of our lesson on determinants and Cramer's rule. We haven't hit Cramer's rule yet, so pause the video, try out some problems on determinants, and then we'll use determinants to apply Cramer's rule to solve some systems. We got more good stuff coming up. Welcome back. You're joining us for part 2 of this lesson. We're going to start right up with Cramer's rule, what it is and how we can use it. So my definition of Cramer's rule is kind of an overview definition. So Cramer's rule I'm defining as a method for solving systems of equations using determinants of matrices. It's not the only method for solving a system of equations using matrices, but it's the only one that uses determinants. So that kind of makes it unique. So how do we use Cramer's rule? Well, let's say that we're given a system, and I'll just do a 2x2 system here just to start small. So let's say we're given a system in the following format. So we have 2 linear equations in standard form, ax plus by equals e, and cx plus dy equals f, where a, b, e, c, d, and f, those are all constants that would normally have numbers filled in for them, and then x and y, those are the 2 variables that we're solving for. So, given this situation, to use Cramer's rule, we are going to first create 3 2x2 matrices. The first matrix, which I'm going to call A, is the coefficient matrix. It has the 4 coefficients in this exact order that they're listed in here for your system of equations. So in this case, we would call those A, B, C, and D. So this would be our A matrix, our coefficient matrix. The next matrix, which I'm going to call B, is basically going to be your coefficient matrix A, but with the x coefficients, which are A and C normally, replaced by the constants. So instead of having A and C right here, we're going to have E and F. We're still going to have B and D, so the only thing that gets replaced is whatever your first variable is, that set of coefficients. Now we're going to make a third matrix. We'll call it C, and this is A, but you might guess what I'm going to say here, with the Y coefficients replaced by constants. So my C matrix, I'm going to have an AC in the beginning now, but instead of a B and D, I'm going to use the E and the F for the Y coefficients. All right, so we've got these three matrices. What do we do with them? So in order to solve the system, we're going to use two formulas that involve these matrices and some determinants. Check it out. To find the X value, we need to take the determinant of this B matrix and divide it by the determinant of the A matrix. So you can think of this as the X matrix divided by the coefficient matrix. And then for Y, we're going to do kind of the same thing, but we're going to use the Y matrix over here, the C matrix, and divide that by the coefficient matrix. So determinant of matrix C divided by determinant of A. So in order to use this practically, you either need to use a matrix calculator or you need to calculate these three determinants and then plug them in the appropriate places. Now just a couple quick words to sort of finish this off before I have you try an example. You might be wondering, well, we only took a look at this 2x2 two-system of equations. Does this sort of process work on anything bigger? And as a matter of fact, it does. For a 3x3 system, you would create a fourth D matrix, and that one would just have the Z coefficients replaced by whatever your constants were, only you'd have three constants at that point instead of just two. You can actually expand this to a system of any size as long as it's a square system, which is to say it has as many variables as it does equations. So you could even do a 5x5 or a 10x10 system using this type of reasoning. The other thing that might come up that's a little bit weird is what happens if you take the determinant of A, specifically the coefficient matrix, and you get 0 for that determinant. Well, that's kind of a deal breaker, right? Because you can't divide by 0. So what does that actually mean? What that means is that the system you are trying to solve either has no solution or it has infinite solutions. We can't really figure out which one. All we know is that it does not have a single one unique solution. All right, are you ready? We're going to have you use Cramer's rule to solve this system of equations. So pause the video and give it the old college try, as they say. All right, so first we're going to set up our matrices, our A, B, and C matrix. And I'm actually going to find the determinants as I go. It doesn't really matter if you set all three of these up and then find the determinants or find them as you go, either way. So let me start with my A matrix. That's going to be the coefficients here, these four numbers. So that's going to be 3, -2, 5, and 4. And the determinant of that, I'm going to have 3 times 4, so 12, minus 5 times -2, so that's a plus 10 in there. So that determinant comes out to 22 when it comes time to plug those in the formula. All right, let's find my B matrix now. That's going to be the A matrix, but I'm going to replace the X coefficients with the constants here, 7 and -3. So we'll put those in there instead of the 3 and the 5. And now the determinant of this one, we're going to have going top down, that's going to be 28. And now we're going to be doing minus -3 times -2. So that's 3 minuses. So overall minus 6 comes out to 22. Well, that's curious. All right, let's do the C matrix. That's going to, again, have our coefficient matrix, only we're going to replace the Y coefficients with the 7 and the -3. And now let's find the determinant of those. So we've got 3 times -3, -9, minus 5 times 7, so minus 35, comes out to -44. All right, so to find the X and the Y values, we're going to do some determinant division. So for X, again, we're going to do the determinant of B over the determinant of A. So 22 over 22 gives us an x value of 1. And then for the y value, we'll do determinant of c over determinant of a. So negative 44 over 22, which comes out to negative 2. And if you want, you can plug them back in just to see if it works. So 3 times 1 minus 2 times negative 4, that does come out to 7. And 5 times 1 plus 4 times negative 2, so 5 minus 8 comes out to negative 3. Boom. And then don't forget to actually write your answer as an ordered pair, so 1 comma negative 2. So after using Cramer's rule to do a 2 by 2 system, it might have been kind of flying around in the back of your head that you might be able to do it faster just using sort of the old techniques that you have, and maybe that's so, but maybe not with a 3 by 3 system, and certainly not with a 4 by 4 or 5 by 5. So as these systems get bigger, having kind of just a very straightforward, no creativity required process like Cramer's rule can make things very efficient. So with that in mind, we're going to go ahead and try this one out here. So we're going to apply the same logic we did with the 2 by 2 system. We're going to create a coefficient matrix, and then you're going to create a matrix for each of the 3 variables. So you're going to have 4 matrices total that you're finding determinants of. And again, with each of the variable matrices, you're just replacing that variable's column with these constants here. So with that in mind, pause the video and see if you can come up with the 4 matrices we're going to need to use, and then stop there because we're going to go through a little bit more about how to use the Desmos matrix calculator. Alright, so let's see which matrices you came up with. So let's start with our coefficient matrix, which we'll call A. So that's going to have 2, negative 3, 5, 1, 4, negative 3, and 3, negative 2, negative 1. So all of that. Next up for B, that'll be our X matrix. We're just going to replace the X column in the A matrix with these constants here. So 12, negative 5, and negative 23 just getting inserted in there. Next up, my C matrix, that'll be for the Y values. So now we're just going to replace the y's in the A matrix with 12, negative 5, and negative 23. And then finally, this one's a little bit new, my D matrix. I'm going to replace the Z coefficients with 12, negative 5, and negative 23. But otherwise, again, just like the others, it's an exact copy of the A matrix except for that one column that we have swapped out, which I've highlighted in red here. All right, so we've got these 4 matrices. How do we quickly find the determinant of these things to help us solve the system? So in the Desmos matrix calculator, and let me show you that. So if you go to desmos.com and you scroll down here, instead of just opening graphing calculator, you'll notice there's actually a lot of calculators you can choose from. Ooh, 3D, that looks neat. But the one that we're interested in today is this matrix calculator. So if you select that, and by the way, this isn't one you'd typically be able to use on a test. It's kind of overpowered for this stuff. But for this higher level stuff, we like to show it off. Let's show how you could use this thing. So in order to use it, you need to create matrices, and then there's some different operations that you can do on those matrices. So what we're going to do is we're going to use new matrix to create a matrix, and then we're going to adjust it to be a 3 by 3. And we'll do that with this A matrix. So we'll do this one together. Let me move this so that I can actually see the A matrix. So we go to New Matrix, click on that, and it automatically names it for you, notice. If you didn't want it to name it A, you could have put some other letter there and then done New Matrix. But in any case, this is a 2 by 2, which is not what we need. So to fix that, notice down here it says Edit Matrix A, and it allows you to customize the number of rows and columns. We want 3 rows and 3 columns, and now we've got the exact dimensions we need. After that, you just need to enter the numbers. Pretty straightforward. So we've got 2, negative 3, 5, 1, 4, negative 3, 3, negative 2, and negative 1. And there it is. Now to use this matrix, you just go to another line and you can do pretty much anything you want to it. You could multiply this matrix by 1/2 if you wanted to. So let me do 1/2 and just arrow over and do A, and hey, now I've got a new matrix that has all of these elements but cut in half. Of course, we don't want 1/2 for this problem. What we want to do is take the determinant. So to do that, there's a little DET button, or you can just write DET. The key is, though, you have to use parentheses. If you use this without parentheses, it's going to pretend it doesn't know what you're talking about. So if you use parentheses and then put in your matrix name, now you can actually get a value out of it. You could also do determinant parentheses and have a matrix in here directly, but it's a lot easier if you just name matrices first and use these matrix variables. So with that handy, and that little tip about using the determinant DET with parentheses, see if you can figure out the values of x, y, and z from these matrices. Pause the video, try it out. Alright, so in order to make this happen, I'm going to need to enter my B, C, and D matrices as well. So let me go back to Desmos, and let me move over so I can see those different ones. So let's do the B matrix next. So new matrix, and it automatically names it B. Still need to adjust the rows and columns, unfortunately. So we'll do 12, -3, 5, -5, 4, and -3. And then -23, -2, -1. Let's make another matrix now, and that'll be our C matrix. Make that 3 by 3. So we've got 2, 12, 5, 1, -5, -3, 3, -23, and -1. The more efficient you get at entering this, obviously, the easier your life is. And then our last matrix, the D matrix, make that 3 by 3. And we've got 2, -3, 12, 1, 4, -5, 3, -2, and -23. All right, so we've got A, B, C, and D all entered. Let's press Enter to get a new line. And now to find the x value, we need to do the determinant of B over determinant of A. That actually has not changed a bit. So let me do determinant of B divided by determinant of A. And that magically comes out to -3. I mean, it's not magic. We know how to find a determinant. We just don't feel like doing all that number crunching ourselves. So -3 is our x value. Next, for the y value, that's determinant of the C matrix divided by determinant of the A matrix. So let me just go here, and I can just replace the B with a C. It's actually kind of nice that I've already got that entered in there. That comes out to 4. Okay? And then finally, for the Z matrix, or for the Z variable, we have determinant of D, where we replaced our Z values, divided by determinant of A. So back in Desmos, replace the C with a D, and that's 6. And then, just like we did with the 2 by 2 system, we're going to write this as an ordered list. So -3, 4, 6. For our last problem, we're going to do a real-life application of solving systems with Cramers. So the molecular mass of a compound is the sum of the atomic masses of the atoms it has. The table shows the molecular masses of 3 compounds, and this is measured in atomic mass units, AMUs. They want us to use a linear system and Cramer's rule to find the atomic masses of bromine, nitrogen, and fluorine. So the basic idea here is we have different combinations of different numbers of these atoms, and we know how many atoms there are in each of these compounds, and we also know what it all adds up to. So we're going to set up 3 equations based on these 3 pieces of information, and then we'll use Cramer's rule to solve that system. And we'll set up the equations together here. So for our first one, we have one of these bromine atoms, so I'm going to write 1B, or just B if you want, either way. And it isn't really clear what order these should go in, so I'm just going to go alphabetically. It looks like we have 0 fluorine atoms here, so we've got 0F, and then we have 3 of these nitrogens, so 3N, and that adds up to 122. So that's the first equation we can write. For the next one, now we have 1B plus 3F plus, there's no nitrogen in that one, so 0N, and that all equals 137. And then finally we have nitrogen trifluoride. That's 0B, 0 bromine atoms, plus 3 fluorine, plus 1 nitrogen, 1N, equals 71. All right, so this is our system of equations. We've solved a 3x3 system before. I'm going to let you pause the video at this point and from start to finish, see if you can figure out the values of B, F, and N. And you can use the Desmos matrix calculator to help you out with this. All right, so if we're going to use matrices and Cramer's rule, again, we need to set up our 4 different matrices. The coefficient matrix plus the other 3 for each of the variables. So here's our first one, my A matrix. That's going to have 1, 0, 3, 1, 3, 0, and 0, 3, 1. Next, my B matrix will have all of this stuff, but I'm going to replace this first column with 122, 137, and 71. The C matrix is going to have all the stuff the A matrix has, but I'm going to replace the middle column with 122, 137, and 71. And for the D matrix, again, I'm using the A matrix, but now I'm replacing the last column, the N column here, with my 3 constants. And at this point, I need to go ahead and plug all of this into my Desmos calculator. So again, here's the matrix calculator. Here's matrix A, 3x3 that I need to make it. So we've got 1, 0, 3, 1, 3, 0, 0, 3, 1, and onto the B matrix, 3x3. That's going to be 122, 0, 3, 137, 3, 0, and 71, 3, 1. Now for the C matrix, 3x3. We've got 1, 122, 3, 1, 137, 0, and I need to see down here, we've got 0, 71, 1. And finally, the D matrix, 3x3, that's 1, 0, 122, 1, 3, 137, and we've got 0, 3, 71. 0, 3, 71. All right, so now we need to do, in order to find B, that's determinant of B over determinant of A. So determinant of B divided by determinant of A gives us 80 atomic mass units. All right, for F, that's going to be C over A. So we'll just go here and replace the B with a C. That's 19, it's pretty light. And then finally, for nitrogen, we need the D over the A. So replace the C with the D. And, oops, that's more than I wanted. Just D, not CD. All right, so 14. That seems a little bit more like it. And that concludes our lesson on determinants and Cramer's rule. Thanks for joining me for some heavy lifting. Until next time, Mr. Sutton signing off.